Equations of motion cylindrical coordinates is the same idea. We're just going to have a different coordinate system. And I'll remind you really quick of what a cylindrical coordinate system is. Cylindrical coordinate system is fixed. So it's not like normal tangential. It's more like rectangular. Except the main difference is the way that we define where a point exists. In rectangular, we would go with two components, an x and a y. That would be rectangular. With cylindrical, we just have one component. Radius is one distance, and then we use theta. So we've got our r and our theta to define the location of a point. The axes that we use in cylindrical coordinates is we have the UR axis, which is just an extension of the radius. You extend the radius out, that is your UR. You're always going in positive extension of that radius. Your U theta is perpendicular to it and always in the direction of increasing theta. Notice my arrow on the theta here is increasing that way, so my U theta is perpendicular to UR, always in the direction of increasing theta. Does anybody know what the third one is for cylindrical? UZ. UZ is the third one. And UZ is the exact same thing as K. There is no difference between UZ and K. We just use UZ in cylindrical. We'll use K in rectangular. So we have UR, U theta, and then a UZ in this case would just be coming out of the board. That would be our UZ. Our equations, I'm sure you could probably guess this part, that we're going to have sum of the forces in the radial direction is equal to mass times acceleration in the radial. Sum of the forces in the theta is equal to mass times acceleration in the theta. And sum of the forces in the z equals mass times acceleration in the z. The reason that we would use cylindrical coordinates is because we've already done some math and introduced our velocity and acceleration. Just a reminder on the acceleration, we have the equation, the radial acceleration is equal to the second derivative of radius with respect to time minus r d theta dt squared. Okay? A theta is equal to r second derivative theta with respect to time plus 2 dr dt d theta dt. And then this one we didn't work with very much before, but az is just equal to the second derivative of z with respect to time, just like we would expect in rectangular coordinates, that the velocity is just the derivative, the acceleration is the second derivative. The nice thing about cylindrical coordinates is we have equations for our accelerations. So if we can fill out the sum of the forces on the left-hand side, the right-hand side is given to us, right? As long as we know something about our r and our theta, the right-hand side will be given to us. So when would you use this? When you have a problem that's giving you information about a particle's motion and you have an r and a theta. Have you seen an r and a theta or an r, a theta, and a z? It's probably a pretty good chance cylindrical is necessary.